I now want to talk about a very important class of matrices that turn out to be pretty useful and pretty interesting in and of themselves. And these are the symmetric matrices. Let's define what they are. A square matrix A is symmetric. Let's put a little squiggly under there. If its transpose is equal to it. In other words, if Aij is Aji for all choices of I and j. So let's look at a few examples. These three matrices here are symmetric. The first one is symmetric because I have this 2 and this 2 are equal. The second one, I have this 2 and this 2 are equal. This 3 and this 3 are equal. And let's use a little rainbow thingy here. This 5 and this 5 are equal. And in this third matrix, this 0 matrix, this 0 and this 0 are equal. It doesn't matter what happens on the diagonal. What matters is that everything is symmetric when you reflect across this diagonal axis. Now let's look at some examples of ones that are not symmetric. These three matrices here are not symmetric. This one, it's easy to see that it's not symmetric. From over here, these 3 and 1 are not equal. Here, although this matrix, the second matrix, is symmetric if we were to flip it across that axis, that does not qualify it to be a symmetric matrix. For a symmetric matrix, it needs to be symmetric when you flip across this axis, which it's not, because this 2 and this 5 are not equal, or also because this 2 and this 5 are not equal. Finally, this third matrix, this 0 matrix, is not even square, so it can't be symmetric. So now I want to explore a few ways that we can actually turn matrices that we already have into symmetric matrices. Let's look at this matrix here. And I want to specifically see what happens when I do A plus A transpose. Well, when I do that, I have 1, 2, 3, 4 plus 1, 3, 2, 4, which is going to be equal to 2, 5, 5, 8. Wow, this is symmetric. Amazing. Wow, I would never have expected that. Not least because I am in a symmetric matrices video. Yeah. And now let's look at this matrix B, and I in particular want to compute B times B transpose. Well, when I do that, I have 4 minus 1, 0, 2, 3, 1, times 4, 2, minus 1, 3, 0, 1. And then when I do the multiplication, I get 16 plus 1 plus 0, 8. Let me move that over to a little bit. 8 minus 3 plus 0, 8 minus 3 plus 0, 4 plus 9 plus 1, which, if I want to simplify it, is 17, 5, 5, 14. And again, this is symmetric. Wow. So amazing. And it turns out that B transpose B is symmetric too. This is not an accident. In fact, we have a theorem! Yay! If A is square, then A plus A transpose is symmetric, and if B is any matrix, then both B transpose B and B times B transpose are symmetric. I'm only going to prove A, but the proof of B isn't very difficult, and it's sort of similar, and I think the book has it in there. Proof of A. All we need to do is show that A plus A transpose is equal to A plus A transpose. That's what it means to be symmetric. So let's do this. Let's calculate that transpose on the left. A plus A transpose by theorem 3.4b, theorem this is equal to A transpose plus A transpose transpose. And then by theorem 3.4, what is it? A, this is equal to A transpose plus A. But A transpose plus A is the same as A plus A transpose because addition is commutative. And that's exactly what we wanted to show. So we can conclude A plus A transpose is symmetric. Tombstone.